All right, so today's topic is from the book, section 2.5, Evaluating Limits Algebraically. We have already started this concept. So not the last lesson, but the previous one to it, you were simply plugging and chugging numbers in from last Friday. If you remember, you would be given a function, you would take whatever the limit is, you would plug it in, and you would get the corresponding y value out. The connection to this has to be the fact that now that we've done talking about continuity and breaks in graphs and things like that, is that all of the functions that you were given then were polynomial in that they were continuous curves. So when you go to draw them, they're like ups and downs. You can draw them from left to right. So here's an example of a parabola. It's obviously in that form of x squared, x in a number, polynomial form. And in the problem, you're asked to find the limit as x approaches -3 from the left. Okay? The connection you're supposed to make here is the fact that this is a polynomial function that has no breaks. So what's coming from the left and from the right is going to be the same thing as the overall limit at 3. So in this case, I can simply take -3 and plug it back into the function. So in here, I'm just going to simply say -3 squared minus 2 times -3 plus 1. But I can't stress enough that that's because you already identified it's polynomial. It's a smooth curve. So when I go to figure this out, I'm going to get a 9 plus 6 plus 1, check my work for me, and I get a 16 out. Okay? So we're kind of working backwards in our thought process. We're saying let's find the evaluation of it, which is also going to be the two-sided limit, which then means that the right limit and the left limit also will work because it's a polynomial. And then we can do the same thing on the right. Here's a simpler polynomial where we're just finding the limit at -5. So I would plug that in, 2 times -5 squared minus 6. Also notice I've chosen problems specifically where we're plugging in a negative, so we have to use parentheses correctly if we're using our calculator. So if we do that, we're going to end up with 50 minus 6, which is going to be 44. All right, so this type we've already been exposed to. We've also seen some examples of rational functions. Okay? So I have a star by this first one because every time we approach a problem, we want to think to ourselves, is this polynomial? Is this absolute value? Is this a step function? Is it a piecewise function? Or in this case, is it a rational function? Rational functions, remember, when we talked about continuity especially, they have two things going against them. They could have, number one, denominators that give them vertical asymptotes, but they also could have factors that cancel that generate a hole in the graph, which is a break in the graph. That doesn't affect the limit as much, but when we go to do the plug and chug method, it does because we'll always generate a 0 in the denominator. However, notice now when I plug a 2 in for x, does that violate the denominator at all? No. So the limit, at this case, what I'm asking you for isn't at an asymptote, and it's not at one of the holes, it's at some other point of x. So we can just simply plug it in, just like we always do, and simplify down to 1. So keep in mind, I could ask you to find the limit at other x values that are not like the special cases involving a rational. Whereas if we move to the next problem, so notice I have this versus because I want to compare them. If I look over here and I plug in a 2, don't I get 0 over 0? This is the part for me, algebraically, that is bad. Having a 0 in the denominator is always a bad situation for me. So we're going to have to use algebra techniques in order to simplify this. The algebra techniques that we want to use are to simply take the top and factor it, x plus 2, x minus 2. Factor the bottom. So to me, this looks a lot like what we were doing when we were trying to identify holes in the graph, which is what we did. We remove the hole from the graph, and then we plug in what's left over. So I'm going to get a 2 plus 2, so this is what I plugged in. So my output is 4. But the connection that we also need to make is while we're answering the question, this graph is going to come along, hit a hole, keep going. Where is the hole at? 2. What is the expected y value at that hole? 4. That is the definition of the limit. So keep all that kind of algebra that we've always done involving holes of rational functions in mind. Any questions on that? All right, so moving down to the next example, we have a much more complicated situation, but identify this as a rational function. So if we're finding the limit as x approaches 3 of all of this, okay? I think instinctually you're going to know that I'm not going to be able to plug this into the bottom without getting a 0. Okay, you could try, but you'll get a 0. So my next step would be to factor. So I'm going to factor. I've got a -3 minus 1. In the bottom, I'm going to have an x minus 3 and an x plus 4, which is going to cancel out the common factors of the whole. Then I can take the 3, which is the x value of the whole, plug it back into what's left. 3 minus 1 over 3 plus 4, and I get 2/7. You will start to get some weird answers for your limits. 2/7 might seem weird to you, but it's a reduced fraction, which is fine. My next value is going to come from this right-hand problem. I think it's pretty obvious if I plug the 3 in, it's going to generate a 0. So I'm going to look to factor the top, which is x minus 3, x minus 3. One pair of them cancels top and bottom. Take this 3, plug it in. 3 minus 3 in this case is 0. Okay. So just as a refresher, don't tell me the answer doesn't exist. It does. This 0 was generated from the numerator. That's not a problem. Okay? And again, if we think of that concept of a whole, my x value of my whole is 3, my y value is going to be 0. So the whole is going to exist on the x-axis.